Hello, everyone. In this lecture, we want to use our knowledge that we discussed in previous lecture to design a custom designed ZKP system using pairing, elliptic curve, and group and field and modular arithmetic knowledge. Okay, so the puzzle in this lecture is uh, asking to find some polynomials. So the challenge here is that if there is a known polynomial like t of x, the question here is that what are four polynomial L of x, R of x, O of x, and H of x in a way that L multiplied by R equal to O plus T of x multiplied by H of x. So we want to follow this puzzle with some examples. So here the polynomial t of x is x to the power of 4 minus 10 x to the power of 3 plus 35x2 minus 50x plus 24. So maybe at the first glance you ask that this is not a meaningful puzzle, right? Finding some four polynomials to satisfy an equation it doesn't mean, right? But in the next lecture, you will see that why such a puzzle is important, and it is actually one of the core bases of the Gross 16 ZKP system. Okay, for this example, exemplify T of x, we are seeking for polynomials that satisfy the equation. Like other ZKP system, there is a prover and a verifier, and the prover claimed that I know those four polynomials. And the red highlight for these polynomials means that these polynomials are secret. Okay, so now the prover wants to prove he knows the polynomials to the verifier. So a naive protocol is to send four polynomials to the verifier, and then verifier check that if L of x multiplied by R of x equals to O plus T multiplied by H or not, right? However, this protocol suffer from two issues. The first one is succinctness. So the protocol is not succinct. So if the size of polynomials is so big, so here for this example, we use some a simplified version of polynomials with just degree of 4. But in practice, if the size of polynomial is, if the degree of polynomials is big, so sending four big polynomials to the verifier is not succinct, right? The other issue that may is more important is ZK knowledge because the prover knows this four polynomial, but the prover doesn't want to share this knowledge with the verifier. So you're talking in concept of ZKP. We are seeking a protocol that prover be able to convince the verifier that I know these four polynomials without sharing these four polynomials to the verifier, right? So now the whole goal of this lecture is to design such a protocol that allows the prover to convince the verifier without sharing the four polynomials. Okay, so to design that protocol, we need some preliminary knowledge. So the first one is Schwartz-Zippel lemma. Okay, suppose that we have a polynomial like f of x, and this is a univariate polynomial of degree d, and we have defined this polynomial in field of f sub p. For instance, suppose this is the formula of the polynomial, and we want to evaluate this polynomial in mod 101. So how we can evaluate the polynomial? So you remember that the field of f sub 101 is a set of element consists of 0 and then 1 and then 2 until 100, right? So if you pick value from this set and replace x by that value, and then compute f of x and uh, compute mod 101, you will reach this blue points. For instance, suppose that you replace x by the value of 0, right? So if you replace x by 0, so this would be 0, this would be 0, 0, 0, and then f of x would be 27, right? So then in location 0, we have 27, and this is the point for the value of x. So if you put value of 1, so then we have 1 here, this is 1, 1, 1. So then you should add 1 plus 12 plus 57 plus 25 plus 27, and then add this value and then compute mod 101, and you will see that the result would be this value, right? So this is the representation of the polynomial in mod 101. And now we want to discuss the Schwarzschild lemma. The lemma says that if you pick a random point from these sets, so here the set is f sub 101, if you pick a random point like tau from this set, the probability that the evaluation of f at point tau equals to 0 is less or equal than d over the size of the field. Okay, let's see how this happens. So here in our example for this polynomial, for 4 points, the evaluation equals to 0, right? For this point, for this one, and this one, and this one. So this might be maybe 11, right? And this one maybe 30, like maybe 34, and this might be 60, and this might be 86, something like that. For this 4 value, the evaluation of f of x equals to 0. So the number of 0, the number of 0, the number of zeros equals to the degree of the polynomial, right? So here the degree of polynomial is 4, and the number of 0 equals to 4. So based on the definition of probability, the probability of uh, that event happen equals to the number of that uh, situation over the whole situation, right? So this means that the probability of polynomial equals to 0, it should be equals to the number of 0, which is d, to the number of all evaluation, right? So number of zeros equals to d, and number of all evaluation equals to the size of the field, right? So then the Schwarzschild lemma says that if you pick a random point from this field and then compute the evaluation, the probability that this evaluation equals to 0 is less or equal than the degree over the size of the field. Okay, now we want to use this lemma to design an equality test. So the equality test says that if you have two polynomials like f and g, and they are defined over field of f sub p, if you want to check that uh, whether f of x equals to g of x, you don't need to compare those two polynomials for all evaluation or check all the coefficient from these two polynomials and then ensure that all evaluation equal to each other and then conclude that those two polynomials are equal to each other. So the equality test says that if you compute a polynomial like h of x, which is equal f of x minus g of x, and then pick a random point like tau from the field and compute h of tau, if h of tau equals to 0, so then you conclude that f of x minus g of x equals to 0, and then you can conclude that f of x equals to g of x. So this is happen if we go back and discuss the idea of Schwarzschild, right? So here we discussed that the h of x polynomial, uh, the probability of this polynomial equals to 0 at a random point like tau is d over the size of a field. In practice, we are using uh, very big values for the size of field. For instance, p is around 2 to the power of 256, and the degree of polynomials in designing circuit using growth 16. So here we are making the basis of growth 16, right? So the d of the polynomials, the degree is less than 2 to the power of 20. And so 2 to the power of 20, so this value in practice, it is around 2 to the power of 40, sorry, I said 2 to the power of 20, 2 to the power of 40 over 2 to the power of 256. And this is a very, very small value. It could be almost 0, right? So the Schwarzschild lemma says that if you have the polynomial like h of tau and then pick a random value like tau and compute the evaluation, the probability of being 0 is almost 0 unless the h of x is already equivalent to 0. And if the h of x is already equivalent to 0, so then you can say that f of x minus g of x is equivalent to 0, and then you can conclude from this equivalency that f of x equals to g of x. So let's review the equality test again. If you have two polynomials like f of x and g of x, and you want to ensure that these two polynomials are equal to each other, you don't need to compare all the evaluation from these two polynomials to ensure that these two polynomials are equal to each other. Just pick a random point like tau and compute the polynomial h of x equals to f of x minus g of x, and compute h of tau. If h of tau equals to 0, so then you can conclude that f of x equals to g of x. So this equality test works in situation that this probability is so small. So this means that the degree of polynomial over the size of the field is very, very small value. Okay, now we want to use this equality test to improve the previous protocol that we discussed already. So you remember that we had a polynomial like t of x. The prover claimed that I know the four polynomials, and then the naive protocol was to send four polynomial to the verifier. But now the equality test says that why you want to send four polynomial to the verifier. So if you just ask the prover to pick a random value like tau, and then the prover sends L of tau, R of tau, O of tau, and H of tau to the verifier, so then verifier can use the equality test to make the evaluation process very efficient, right? So let's review the equality test again. So equality test says that if you have two polynomials like f of x and g of x, and you want to check that if they are equal to each other. So suppose that we consider this as f of x, and we consider this as g of x. So in original protocol, the verifier obligated to check that if f of x equals to g of x or not. But now we say that the equality test says that just compute f of x minus g of x and just calculate uh, h of tau to see if it's equals to 0 or not, right? So the verifier just need to compute L of tau, R of tau, O of tau, T of tau, and H of tau, and then check this equality test. And if it's satisfied, so then the verifier convinced that the two sides of the equality are equal to each other, and then conclude that the f of x and g of x are equal to each other. So this means that the left and right side of the equation are equal, and then the prover really knows the four polynomials. Okay, so then for this exemplified polynomials, uh, the verifier sent tau equals to 5, and then prover computes L of tau. So this is the polynomial L of x, and if you replace tau x equals to 5, so then L of 5 equals to -4. And then the, the prover sends these values to the verifier, and then verifier by himself compute t of tau, because the polynomial of t, this is a public polynomial. It is not a secret, so verifier knows this polynomial. So then the verifier computes t of tau, and then replace this value in the equality test, and then ensure that this equality test is satisfied, right? So since this equality test is satisfied, the verifier concludes that the prover really knows those polynomial, right? Okay, so this polynomial is succinct. So if you compare this protocol with the previous protocol. So in this protocol, the prover just sent for evaluation, not the whole four polynomials to the verifier, right? And also in the verification round, the verification test is very faster than evaluating uh, equality of five polynomials. So this succinct protocol, however, is suffering from another concern, and that is the soundness concern. So the concern here is that how we can guarantee that the prover really send the exact evaluation to the verifier, right? So here the question is that what if the prover sends some other evaluation to the verifier? For instance, suppose that a prover doesn't know the four polynomial, right? So the prover just sent the random value that satisfies this equation. For instance, the prover sent for L of tau maybe 2, and for R of tau maybe 4, right? And then for O of tau maybe 7. For T of tau it is equals to 24, and then for H of tau 1 over 24, right? If these four values are picked by the prover and sent to the verifier, so these four values also satisfy this polynomial, right? However, the prover doesn't need to know any specific polynomials or any knowledge. But in the verification side, the equality test is satisfied, so then verifier is convinced that the prover knows the polynomial. And this is not correct. So this is the soundness concern. We need to ensure that prover really knows the polynomial, and then using those specific polynomials, compute the evaluation and send the evaluation, not just uh, specific designed values without knowing the polynomials. Okay, now the question is that how we can guarantee that prover knows the polynomials and compute the evaluation based on those polynomials. So here we want to define another technology, and this is called commitment scheme. A commitment scheme is a cryptographic primitive that allows a person like a prover to commit to a specific value. So this specific value could be a message, could be a polynomial, or any other kind of data. So later, this person could do some computation or some claim based on that specific value without leaking that specific value. For instance, when we are concerned about a knowledge of a polynomial by a prover, a commitment scheme allows us to bind a prover to a specific polynomial and then really do the computation and evaluation of those bind polynomial. And this is the features that commitment scheme guarantee. So now we want to use commitment scheme to improve the previous protocol to address the soundness concern of it. Okay, a commitment scheme, as we discussed, provides two properties, hiding and binding. So hiding means that from a commit value, you cannot retrieve the original specific value or the original polynomial. And also, the binding guarantee that if the prover do some computation, it would be definitely given from the polynomial. The prover would be bind to that specific polynomial. Okay, let's see the example for the commitment scheme. So to do the commitment scheme, we need all the previous knowledge that we discussed in previous 4 lectures. So the concepts of field, the concept of proof, the concept of elliptic curve, and the concept of pairing. So this means that we actually discussed 4 previous lectures to just be able to design a protocol for this specific puzzle. The puzzle says that who knows 4 polynomials that satisfy this equation, To design this specific ZKP protocol for this specific puzzle, we needed all of those previous knowledge. So now we want to use that knowledge to address the soundness issue in the previous protocol, and then done. Okay, so let's see how using the previous knowledge we can design a commitment scheme. So here, when we use a commitment scheme, so then the prover does not send the evaluation of the polynomials or the polynomials to the verifier. The prover just sends the commit of the polynomial to the verifiers. Okay, so let's see how our commitment scheme works. So in this, there are so many different commitment scheme solutions, but in this specific commitment scheme, we need a trusted authority that needs to do some computation. The first step is that the trusted authority run the key generation algorithm. So the trusted authority decide the value of P, which is the prime number. So you remember that in previous discussion, we always use 101 as the prime number. So based on this prime value, the trusted authority also decide a specific elliptic curve, and then using that specific elliptic curve and the prime value generates G1 with the generator of G1 and G2 with the generator of G2, and a pairing that pair the value into a target group. So the previous G1 and G2 in the previous slide. So yeah, so these values, the G1 and G2 with the generators and with the veil pairing function that we discussed, all of those computation and knowledge are picked and chosen by the trusted authority here in the key generation algorithm. So then the protocol says that the trusted authority should pick a random value like tau from the field and consider it as a secret, and then publish some values that we are called SRS. So as the first element of SRS equals to G1, which is the generator of the first group, right? So this is G1. So the second element of the SRS is tau multiplied by G1. The tau is picked here in previous step. So then after running the key generation algorithm by the trusted authority, the prover needs to run a commitment algorithm. So the commit algorithm at the first step says that compute the polynomials in mod n, and n is the torsion of the elements when we are computing the pairing. So we discussed the value of torsion in previous lecture, right? And then using this formula, the prover compute the commit of different polynomials. For instance, the polynomial L of x, which is written in form of L sub 0 plus L1x plus L2 blah blah. So it should be the prover used this formula to compute the commit of the polynomial. Okay, so then the prover send this commit value instead of evaluation of L of x or the L of x to the verifier. Okay, at the verification round, now we want to see how the verification algorithm change. So you remember that we at the first protocol, the verifier needed to check that if the equation is correct by multiplying the polynomials and then uh, check that if the left and right side are equal to each other or not. So in the first protocol, the prover sends those polynomial to the verifier, but later we discussed that that is not a good solution. So then we discussed that instead the prover uh, send the evaluation of the polynomial at point tau and send it to the verifier, and verifier check this equation instead of checking the equation for the polynomial. And then the equality test guarantee that if this equation is correct, so then the prover knows the knowledge. However, now we see that the prover does not share the polynomials or the evaluation at point tau to the verifier. So the prover just sent the commit of the polynomials to the verifier. Now we want to see how using commit verifier can ensure that the prover knows those polynomials. Okay, so the verification algorithm says that you need to multiply the two sides of this equation by G1. And G1 is again is the generator of group 1, which is known by the public. So the left side is multiplied by G1, the right side also is multiplied by G1, and then we know that each of these two values equals a point in the group G1, right? Because this is a scalar value. So suppose that L of tau multiplied by R of tau could be like maybe 6, and O of tau plus T of tau multiplied by H of tau equals to 6, right? 6 multiplied by a point in a group is another element of group G1. So then here the algorithm says that when you have two elements from group G1, you can compute the pairing of these two elements with an element from G2, right? So let's go back to the concept of pairing. So yeah, here. So here, the verification algorithm says that if you have 2 points like these two to each other, and you want to ensure that if these 2 points are equal to each other, instead of comparing these 2 points to each other, you can compute pairing of any of these 2 points with another point from the group G2, right? So for instance, you compute pairing of the first point with the point from group G2, and again pairing of the other point with the point from group G2. And if the two pairing value are equal to each other, so then you conclude that these 2 points were already equal to each other. So our verification algorithm used from this property. So the verification algorithm says that you want to see that if these two left and right side, that they are two elements from G1 are equal to each other or not. So to do that, to check that, you can compute the pairing of the left with G2, which is the generator of group G2, and pairing of the right side with G2. Okay, now we want to simplify this formula. So you remember this property from the previous lecture. So if you have a scalar that is multiplied by the first element at the pairing, you can change this scalar value as considered as a power, or you can put the value, the scalar value here. Or maybe even you can put half of this n uh, at the power or at the scalar for q. For instance, you can have this value e of like maybe p and n over 2 q and 2 times here, right? You can have this also. Okay, so based on this property that is satisfied in pairing, we want to change this formula into this one. So this formula says that uh, pick this part from the first element and consider it as the scalar for the second element. So now we have R of tau as the scalar for the second element of the pairing at the left side. On the right side, we does not have any change. Okay. After this updating the formula, so then we say that okay, the L of tau multiplied by G1 is the commit of the polynomial L of x on group G1. So like this formula. So like this formula. So L of commit of L of G1 equals to L of tau multiplied by G1, or this is equals to L0 multiplied by G1 plus L1 tau G1 blah blah by this formula. So this value already is computed by the prover and is sent to the verifier. So the other one, the second part also is the commit of polynomial R of x, and it is computed by the prover and is sent to the verifier. And this part also is commit of the other polynomial, and it is computed by the prover and is sent to the verifier. So then the verifier just need to compute this pairing to ensure that if this pairing satisfied or not, right? Okay, so then let's review the algorithms again. In the first protocol that we have designed, we mentioned that the prover needs to send 4 polynomials to the verifier, and the verifier check this equation to ensure that if it's correct or not. In the second protocol, we mentioned that the prover sends the evaluation instead of the polynomials to the verifier, and the verifier check this equation to ensure that prover is correct. But in the third protocol that we are discussing now, the prover does not share the polynomials or the evaluation of the polynomials. The prover sends the commit of polynomials. And then the verifier check this pairing computation instead of equality test in previous protocols. And if this equation is correct, the pairing on the left side and the pairing on the right side are equal to each other, then we say that, okay, uh, the the prover really knows the polynomial, right? Okay, so now we want to follow this protocol and algorithm using our exemplified polynomials and the group that we discussed in previous lectures. Okay, so let's see the exemplified group and yeah. So at the trusted authority at the key generation round first needs to pick the prime value. It would be 101 as we discussed in previous lectures, and also an elliptic curve. That's the formula equals to y to the power of 2 equals x to the power of 3 plus x plus 9. This is actually the elliptic curve that we used in our previous discussion in the previous two lectures, right? And then the torsion value for computing the pairing is 119. We also discussed this value in previous lecture. So we have two groups here, the group G1 with generator of G1, 4 and 28, and group G2 with the generator of G2, right? So the previous group, right? So this was the groups. Group G1 with the first generator and group G2 with this generator. And this is the generator for the first group. Okay, now we use this knowledge to follow our protocol. So the next step is the trusted authority pick a random value for tau. So now we assume that the value of tau is 5, and this value should not be shared by the prover or verifier, especially the prover, and this value should be saved as a secret. We will discuss later why. Then the trusted authority computes the SRS value and share it with the public. So the first element of the SRS is G1. So G1 is this value, 4 and 28, right? So this is the first element. So the second element of SRS is tau multiplied by G1. So the second value, so this one, equals to 5 times 4 and 28. Okay, so what is the multiplication of 5 and with the point 4 and 28? So this is actually the scalar multiplication in elliptic curve, right? We can use from our website to compute this multiplication. Okay, so let's use our website from here on the elliptic curve cryptography part over the field. So here the prime value is 101, and 1 and 9 are the parameters for the elliptic curve. Now we want to compute the scalar multiplication, right? 5 times of 4 and 28, right? 5 times 4 and 28, it is equal 19 and 9, right? So we computed this value, 5 times 4 and 28 equals to 19 and 9. 90 and 9, right? So this is the second element, right? The third element equals to tau to the power of 2 multiplied by G1. So tau to the power of 2 equals to 25 multiplied by 4 and 28 And if you use the website and compute this multiplication, you will see that the value equals to 90, 59 and 666. And then compute the value of tau to the power of d minus 1, and d equals to the degree of the polynomial c of x, which is 4. So d minus 4 equals to 3. So 5 to the power of 3 multiplied by 4 and 28. And this is equals to 71 and 42, right? Using the website, you can check that this computation is correct. Okay, now the key generation round is completed. The responsibility of the trusted authority is done. The prover now needs to follow the commit algorithm. Okay, so let's raise this value. Okay, so the first step is that the prover computes the polynomials in mod n. So the value of n equals to 119. So the polynomial should be computed in mod 119. So the prover already knows the 4 polynomials, and the coefficient in those 4 polynomials are float values. So it should be computed in mod 119. So let's compute one of the values to see how this equation, this coefficient are computed in mod 119. For instance, we want to see how minus 1 over 3 is converted into 79, right? Okay, what is 1 minus 1 over 3? You remember from our discussion in lecture 2, 1 minus 1 over 3 equals to minus 1 multiplied by the inverse of 3, right? What is the inverse of 3 in mod 119? Again, we can use from our website in parts modular arithmetic. We want to compute the inverse in mod 119. So the inverse of 3 in mod 119 equals to 40, right? Okay. Yeah. Okay. This equals to minus 1 multiplied by 40, right? Now we want to compute minus 4d in mod 119, right? So let's see what is this value. So the modular arithmetic, 119 and minus 40 equals to 79, right? So it was equals to 79, right? So then the computed value for 79 is correct, and I have shown how to convert the coefficient minus 1 over 3 in mod 119. You will compute this with the same process and see how 5 over 2 equals to 62 in mod 119, and how minus 31 over 6 equals to 94 in mod 119, right? Okay, now the first step is done by the prover. So the second step is that the prover needs to compute the commit of the polynomial. So the formula to compute the commit says that the prover can compute the commit by two formula. The first formula equals to L of tau multiplied by G1, or the prover can use from this formula. So by any of these two formula, the value of commit could compute it correctly. Okay, so let me pick the pen. Okay, now we want to see what about the first formula. So for the first formula, the prover needs to compute L of tau. So this is L of x, and the prover just need to replace the value of x by tau and then compute L of tau. But the problem here is that prover doesn't know the value of tau, right? Because the value of tau is a secret that the trusted authority does not share with the prover. So then the first formula cannot be used. So then the prover used the second formula from this one to compute the commit of polynomial G L of x, right? Okay, so the formula of the commit says that if you write the polynomial L of x in this form, so then you need just to multiply the coefficient of the polynomial with the SRS values, right? So let's see how this happens. So the formula says that so this value is to L sub 0, right? So the formula for the commit says that the L sub 0, which is 4, should be multiplied by G1. So, and G1 also equals to the H10, so this value. So L0 equals to 4, and it should be multiplied by H10. So the second element is L1. So L1 equals to 94. 94 multiplied by tau multiplied by G1. So how prover knows the value of tau multiplied by G1? It is actually the value that already computed by the trusted authority and shared here in the SRS. Tau multiplied by G1 equals to H11, right? So then this value would be multiplied by H11. The third element equals to L2, and this is L2, 62, right? Multiplied by tau to the power of 2 multiplied by G1. And the value of tau to the power of 2 multiplied by G1 already computed by the trusted authority, and this is H12, right? So this is multiplied by H12, and then for the next one also multiplied by H13, right? So this means that the prover used the SRS value that already computed and shared by the trusted authority to compute the commit of the polynomial. Okay, now the prover needs to compute this value. So 4 times of H10 equals to 4 and 28. H11 equals to 90 and 9, and then this value, right? Now the prover needs to compute this values. Okay, how prover compute this? Again, this is just a scalar multiplication and addition of the elliptic curve points, right? So again, the prover can use from our website. So the first step, at the first step, the prover needs to compute this value 4 times of 4 and 28. So this one, right? First, the prover do this multiplication. 4 times of 4 and 28. So let's use our website. So in the elliptic curve over f sub p, so the curve and the prime are set already. So just put 4 here, 4 times of 4 and 28. 4 and 28, and it equals to 27 and 78, right? 27 and 78, right? So the next multiplication equals to 94 multiplied by 90 and 9. So 90 and 9 and equals to 71 and 59, right? 71 and 59, okay? So the first multiplication is done by the prover. Okay, after the prover compute this multiplication, this one, and this one, so now prover has these 4 points that should be added to each other. And now the prover use the point addition tool in our website to add this point to each other, right? So the prover add these 2 points first to each other, 27 and 78, 27 and 78 plus 71 and 59, and the result equals to 48 and 16, right? 48 and 16, right? 48 and 16. Okay, now again, the prover used from the website to add these 2 points to each other. So the result would be 4 and 28. And then finally, prover used the uh, point addition tool to add these 2 points to each other. And the final value would be 4 and 73. So this is the commit of polynomial L of x. Okay, so let's review what happened here. So we discussed in the first protocol, the prover send the polynomials to the verifier, right? In the second protocol, we mentioned that the prover send the evaluation of the polynomial to the verifier. But in the third protocol, the prover sent the commit of the polynomials to the verifier. So the commit of polynomial for the L of x polynomial is this value, right? 4 and 73 to the verifier. So this commit provides 2 properties. So the first property is hiding. From this just point of the elliptic curve over f sub p, the verifier cannot retrieve this polynomial. It is impossible for the verifier to retrieve the polynomial from the commit value. The second property is that this commit value is really computed based on the polynomial, because if the prover do any cheat and send another point as the commit, so then the pairing would not be satisfied. So this equation would not be satisfied. Okay, so now the prover send the commit value to the verifier, and the verifier needs to check the pairing to ensure that mm, the knowledge, the claim knowledge by the prover was correct. However, to compute the pairing on the left side and the right side, the commit of L of x is not enough, right? The commit of R of x, also the commit of O of x, and the commit of H of x, they are also needed to be computed by the prover and sent to the verifier. So then this protocol should be extended to compute the commit for other values by the prover. Okay, now we want to extend and improve this protocol. So we will add some extra knowledge in the trusted authority responsibility, and also for the prover to provide all of the three values as the commit value for the verifier. Okay, so this part is repetitive, the initial steps. This part is the tau random and secret value. So now we say that the trusted authority should generate SRS. So this value already computed by the trusted authority, right? So other than the SRS1, the trusted authority needs to compute SRS2 also, and also SRST with this formula. So these values are needed for the prover to compute the commit of other polynomials. Okay, so let's review these values. So G2 is the generator of the group number 2, right? So this is G2, and G2 equals to 89 plus 51i and 63 plus 93i. So this is G2, the generator of the group number 2. So the second element of the SRS2 equals to 2 multiplied by G2. So tau multiplied by G2, and tau is 5, right? So this means that we need to compute 5 multiplied by G2. So let's use our website to compute 5 multiplied by G2. Okay, now G2 is the generator of the elliptic curve over the extended field. So we need to use from here, right? And then the scalar multiplication. So 5 and G2 equals to 89, 51, 63, 93. And the value equals to 33 plus 60i. So 33 plus 60i, and 48 plus 81i. 48 plus 81i, right? So this is the value of 5 multiply G2, right? Okay, now the second element, the third element in the SRS2 equals to tau to the power of 2 multiplied by G2. So tau equals to 5. So this would be equals to 25 multiplied by G2. And again, you can use from our website to compute 25 times of G2, and you will see that this would be the result. And the final value equals to tau to the power of 3, which is 125, and 125 times of G2 using our website, you will see that it would be equals to this value. Okay, for SRST, the trusted authority follow these formulas. So G1 multiplied by T of tau. So this is the polynomial T of X, and T of tau, the trusted authority computes T of 5 equals to 5 to the power of 4 minus blah blah, and computes some values, and then multiply it by G1. So G1 is the generator of the group G1. So the prover will follow the same computation and our tools in the website to compute this value, and then the value would be this one and this one and this. You can check using our website to ensure that these values are correct. Okay, so we already discussed how prover compute the polynomial L of x in mod n, which is 119. So prover will do the same thing and compute the other three polynomial in mod 119 with the same method that we discussed already. Now the prover needs to compute these two other elements to be sent to the verifier. So the commit of L of x already computed. The commit of R of x should be computed now. So the commit of R of x would be computed by the SRS2 values. So H20 is this one, H21 is this value, H22 is this value, and H23 is this value. And these are the coefficient of the polynomial, right? Like Tony is this value, the coefficient, and 117 is this coefficient. Using the coefficient of the polynomials and SRS value, the prover will compute the commit of polynomials. So with the same pattern, the prover compute the commit of O of x by this part, and commit the commit of h of x tau of x by this formula. So again, the prover needs to do the scalar multiplication for the points of the group, and then do the addition of the points, like we discussed when we compute the commit of polynomial L of x. Now these three values for the polynomial, so these three values would be sent to the verifier, right? So these three values would be sent to the verifier, and then the verifier will check that if the pairing of these two left and right side are equal to each other or not. Okay, so now let's compute the pairing value to ensure that if they are correct or not. Okay, so let's see here. Let's remove this. Okay. Okay. Now we want to compute the pairing value again using our website. So the left side says that the verifier needs to compute the pairing of commit of L of x. The commit of L of x equals to 4 and 73, okay? And the commit of R of x, which is this value, right? So first we want to compute the pairing of these two values. Okay, if you remember, this pairing was actually the pairing that we computed in previous lecture, right? So if you recall the previous lecture, we computed the pairing of these two elements, and it was 98 plus 48i. And we also can use from the website to compute this pairing, right? Okay, so let's use the veil pairing part. So, and then we want to compute the pairing. So the pairing of 4 and 73, okay, these are actually the default value on our website. And 92 plus 53 and 6 plus 7 are. So the result equals to 98 plus 48i, right? 98 plus 48 I. Now we want to compute the pairing for the right side. So the pairing for the right side is pairing of the commit values, which is 50 and 83, and G2. And the G2 equals the generator of the first group that is shared already, right? Okay, so the pairing of 50 and 83, so let's compute it, 50 and 83. And 89, 51, 63, and 93. So the pairing equals to 98 plus 84i, right? So which is equals to 98 plus plus 48i. So now we see that the pairing of the left side and the pairing of the right side, they are equal to each other. And then the verification test is passed. So then the verifier is convinced that the prover really knows the polynomials. Okay, so let's review the protocol again. So the first protocol, prover sends the uh, polynomials to the verifier to prove that he knows the polynomials. But we discussed that this is not a zero knowledge and succinct protocol. So then we switch and use a Schwartz-Zippel and equality test and mention that just sending the evaluation at a random point like tau to the verifier is satisfied. But later we discussed at the second protocol that there is no guarantee that the prover really knows the polynomial and do the computation given from the polynomials. So then we use the commitment scheme to guarantee the succinct, to guarantee uh, the prover could not cheat. And then the third protocol says that prover needs a trusted authority to decide an elliptic curve, pairing, groups, and compute some SRS value, and then prover compute the commit values instead of evaluation or the original values, and then send the commit values to the verifier. And at the verification side, the verifier just need to compute two pairing and done. So we see that all of our previous knowledge about pairing, modular arithmetic, elliptic curve, and um, group and field, all of those knowledge are needed to design this commitment scheme, right? Okay, so now let's discuss why the value of tau should be secret, and it should not be shared by the trusted authority. Why this is important? Okay, suppose that the trusted authority cheat and share the value of tau with the prover. Now we want to show that how, by knowing the value of tau, the prover could pass the pairing test without knowing the polynomial. Okay, so we assume that the prover knows the value of tau. So then the prover, while doesn't know the L of tau, R of tau, or those value, L of x, R of x, and those value. So the prover just mm, compute some random value for L of tau, R of tau, O of tau, and H of tau in a way that this this test is passed, right? So prover compute this value without knowing polynomials. So any value that satisfies this equation is accepted. You can pick some other values, like you can put 2 or 4 and then put other values here in a way that this equation is passed, right? So here we see that the prover doesn't know the polynomial, right? The prover just the prover just pick values that satisfy the equation. So the prover doesn't know the polynomials, so doesn't do any computation over mod n. And then since uh, the prover knows the value of tau, so then the prover can compute the commit of the polynomial using from this formula, L of tau multiplied by G1. So if the value of L of tau is this one, and then this is the fake values for the sorry, I made a mistake. So these values, they are the correct evaluation of the polynomials L of x, R of x, O of x at point tau. So now we want to assume that the trusted authority knows the value of tau and generates some fake values for uh, for the evaluation of the polynomials, right? So if the prover knows the value of tau, so then the prover could compute T of tau using this formula, right? And I can understand that the T of tau equals to 24. So then by knowing this value, the prover can generate some other fake values for the evaluation of the polynomials L, R, O, and H. So you see that these are the correct value from the polynomial, but when the prover knows the value of tau, it can compute the T of tau and then decide these four fake value in a way that this equation is passed. Now the prover used the second formula to compute the commit of polynomials. So instead of following the this formula, so the prover used this formula to compute the commits. Just L of tau, which is 12, multiplied by G1, which is 428. And then by computing this value from the website, the commit of the fake polynomial equals to 55 and 30. So with the same formula, the prover computes the commit of R of tau, and then the commit would be this value, and then the prover compute the commit for the third polynomial O and HT using the fake evaluation and this formula. So now the prover send this fake 3 commit to the verifier. And if the verifier computes the pairing at the left side, pairing of these two values, and pairing at the right side, so verifier see that these two pairing are equal to each other, right? You can check this equality using the website to ensure that these fake commit are satisfied the verification test. So we see that the prover knows the value of tau from the trusted authority and computes T of tau and then generates some fake value for L, R, O, and H of tau, and then use the other formula to compute the commits and then convince the verifier that he really knows the polynomials. And this is not correct. So that's the reason the authority should be trusted and do not share the value of tau with the prover. Okay, and then this is the reason that we assume that the trusted authority will burn the value of tau and will not share it with nobody, especially with the prover. Okay, now we want to review our process, the generated, the discussed design protocol for this specific puzzle. So let's review the puzzle again. So there is a polynomial like t of x, and the question here is that who knows four polynomial L, R, O, and H in a way that L multiplied by R equals to O plus T of x multiplied by h of x. First, we discussed the naive protocol, and we said that the prover can send 4 polynomials to the verifier, and then the verifier check the equality to ensure that the left and right side of the polynomials are equal to each other, right? So we discussed that this protocol is naive and is suffering from succinctness because when the size of polynomial is big, prover is obligated to send so big polynomials to the verifier. The other concern is ZK. Prover doesn't want to share the knowledge with the verifier. So first we solve the issue of succinctness. And we mentioned that if we using the equality test that is designed based on Short-Sippel lemma, we discussed that the prover doesn't need to share the polynomials to the verifier. Just the verifier pick a random value and then the prover share the evaluation of those polynomials to the verifier. And then if this equality test is satisfied, so then verifier convinced that the prover knows the polynomial. However, the concern was that the soundness concern. What if the prover really compute the evaluation using the polynomial? So we saw that the prover can generate fake evaluation and convince and pass the test. So then we use all of the knowledge from previous lecture 2, and then lecture 4 and lecture 5, and then these 2 knowledge that we discussed in this lecture. So to design a commitment scheme. So the commitment scheme allows the prover to just send the commit of polynomials to the verifier instead of sending the polynomial or the evaluation of the polynomial. And then verifier do the pairing test to ensure that the prover really knows the knowledge, right? Okay, so now we want to see that if this is a ZK SNARK protocol or not, right? So this protocol provides succinctness, right? Why? Because the prover just sent 3 commits of the polynomials. And you know that the commit of polynomials are just element of group G1 and G2, right? So no matter how much is the polynomial is big or what is the degree of the polynomials, at the end of the day, the commit of polynomials is just an element from group 1 or group 2. So then the size of sent proof is very succinct. Other than the size of proof, the verification algorithm also is fast. The verifier just need to compute the pairing of 2 elements 2 times. That's it. So then this protocol is succinct. So the other property is zero knowledge, right? So the prover doesn't share the polynomials with the verifier, and using the commit of polynomials verifier would not be able to retrieve the polynomials. So then zero knowledge is guaranteed. So the other property is non-interactivity, right? So the prover and verifier doesn't need to interact with each other, and then the protocol would be public verifiable. Everyone could run this pairing test to ensure that prover was correct. So since this property is guaranteed, so then the third protocol is a ZK SNARK protocol, right? Okay, so let's review very quickly again. So we at the first protocol, the prover at the first protocol, the prover sent the polynomials to the verifier, right? So this means that we discuss at the plain text space or scalar space. But at the final protocol, which is the accepted and correct protocol, so the prover send the commit of the polynomials and we discuss in the field domain. So this means that if we switch from the scalar space into field domain, the prover doesn't need to share the evaluation of the polynomial or the polynomial and just share the commit of polynomial, and then using the pairing, prover could convince the verifier, right? And to switch from the scalar space into the field space, we actually needed all of those knowledge that we discussed in previous lectures. Okay, so we discussed 4 lectures already to finally design this specific protocol for the polynomial, right? So now maybe you ask that this is not a meaningful puzzle. So why it doesn't matter that knowing 4 polynomials in a way that satisfying this equation is a valuable puzzle. Why we had overview all of those knowledge in previous 4 lectures and then design this protocol for this specific puzzle. Yeah, this is a correct question. In next lecture, you will see how we can modify and use this specific design protocol to finally discuss growth 16. This specific design protocol is actually a big main part of growth 16. Okay, in next lecture, you will see how. Thank you and see you on the next lecture.